Can you solve this infinite expression? It looks impossible, but the trick is in the repetition. This type of representation is known as a continued fraction. This one is simple. Let's try solving it. The trick is to notice that since this fraction repeats itself indefinitely, we can simply replace this part with x. Now, if we rearrange, it becomes a quadratic we can solve. You may recognize this quadratic. It's satisfied by the golden ratio, phi. We can apply the quadratic formula to solve it, and we get 1 plus minus the square root of 5 on 2. We know the plus root is the correct one here, since our original expression showed x was positive. So, this is the continued fraction for phi. Cool, right? But does it have any actual use other than just a strange representation? As it turns out, we can use the continued fraction to generate very good rational approximations of phi. If we just end the fraction early and tidy up the fraction, we get this, which is correct to 1 decimal place. So, phi's continued fraction is tidy, but pi's? Well, brace yourself, the numbers now appear to be completely random, but notice how this number is a bit bigger than the rest? Since 15 is relatively large here, 1 over 15 will be very close to 0. This means, if we stop this continued fraction right here, we should get a very accurate approximation of pi, and if we do this we obtain the famous 22 over 7. If we look ever so slightly farther into the fraction, we see 292, which is even larger than all the previous numbers. If we once again say that 1 over 292 is approximately 0, we get the slightly less well-known approximation, 355 over 113. Let's go back to our continued fraction for phi. All the numbers here are 1, which is the smallest a number in a continued fraction can be. As a result, if we stop the fraction anywhere, we will always create a large amount of error in our approximation. This leads to phi being very hard to rationally approximate, and is one of the reasons why people refer to it as the most irrational number. We've seen how sometimes the continued fraction of irrational numbers can be very orderly, like in phi, but also how the continued fractions can be seemingly completely random, like for pi. But are the values truly random, or are some numbers more probable than others? Let's put all the values which appear in the fraction in a list, like so. If we take the geometric mean of these numbers, which means that we multiply them all together and we raise it to the power of 1 over n, where n is how many numbers there are, the results turn out to approach a value, about 2.685. So all the numbers will have values which should be somewhat close to this value. Some will be higher and some will be lower, but they will average each other out. What if we try this trick for another interesting number? Let's take the Euler-Mascheroni constant, gamma, which is a constant related to the gamma function. It doesn't matter what this number is, and that might be a video for another time. This number is about 0.577, and here's its continued fraction. Let's put them in a list and take the geometric mean again, and that's funny, we get exactly 2.685 again. So what is this mystery number? It's believed to be Khinchins constant, and almost all real numbers have the property that the geometric mean of their continued fractions approach this value. However, nobody has ever proven that it does hold true for pi, but numerically it appears very convincing. This appears to be the case for loads of well-known constants, like the cube root of 2, logs of numbers, Apéry's constant, and even Khinchins constant itself. But the proof that any one of these numbers actually has this property has evaded us. However, there are exceptions to this rule. Clearly phi from before does not have this property. All of its values are 1, so the geometric mean will also be exactly 1. It turns out all numbers which are solutions of quadratics are exceptions. The biggest exception, however, is Euler's number, which, like phi, has quite a simple continued fraction. Since it includes the even numbers which are increasing, the geometric mean will just keep increasing too. If you enjoyed diving into the hidden patterns of irrational numbers, consider subscribing. If you want to see more videos like this and you have a topic you want me to cover next time, comment that down below. Thank you for watching.